All right, guys, can I get a thumbs up that you hear me and see the board okay? All right, here we go. So these important components, your vertical asymptotes, your horizontal or oblique asymptotes, okay? So if we look here, in the first question, they ask you to find the domain of each rational function and then identify, if any, the vertical asymptotes. So remember, your domain is an important part of the puzzle because it's basically telling you who the bad guys are. Who are the x values that you would never want to plug into this function? So remember, when in terms of domain, the two things we look for are dividing by zero and negative numbers under even root radicals. So radicals don't come into play because we're working with polynomials, so we shouldn't see any radicals anywhere. All right, but we definitely have to watch out for dividing by zero. So if you look at this function, if I have to find its domain, right? Well, in the next section, guys, when we start actually putting his entire graph together, I'm going to give you like a laundry list of steps of things that you're going to need to do. Your step one is always something called FDR. I'm going to make you factor the rational expression. I'm going to make you find your domain, and then I'm going to make you reduce it. So I want you guys to get into that habit, so I'm going to do that. Even though we're asked to find the domain, this is still part of the process. So you would look to factor. Luckily, nothing factors. So then you would find the domain. Always find the domain before you cross anything out and simplify anything. So as far as your domain is concerned, I never want the bottom to become zero. So I never want x minus 5 to equal 0. So take the bottom and tell me x minus 5 can never equal 0. Now go find the number that does make it equal 0, and that would be 5. So that means 5 is a number that you would never plug into this function, because then it would be 8 divided by 0, which is an undefined operation. It doesn't create a point for you to put on its graph. All right, so the domain would be written. I think they ask you for interval notation. So in interval notation, the smallest number x could be is negative infinity all the way to 5. Take 5 out using a parenthesis. Union, pick up on the other side of 5, and then it shoots off to infinity. Any number from 5 to infinity is in your domain. Okay. Well, guys, I know they don't ask you for all the holes or whatnot, but it's just part of the process, so I'm going to talk about a little bit more. So now you know who the bad guy is. It's 5. Since nothing canceled out and reduced, 5 is still forever and always going to look like the bad guy. I definitely don't want to plug 5 in. So that means since the graph cannot exist when x is 5 because you're not allowed to plug him in, that's going to create a vertical asymptote when x is 5. It acts like a brick wall where your graph doesn't exist. So that means we're going to end up with a vertical asymptote at the line x equals 5. Now remember, your domain, you're telling me x cannot be 5. But when you're talking about the vertical asymptote, x equals 5 because that is the line where that vertical asymptote is going to exist. Every year I have students who want to do this for the VA, but that's not the case. The VA, you're writing an equation for that bad line, if you will, okay? All right, now I want to talk about this. Any number that is not in your domain, in this case it's just 5, any number not in the domain, we saw yesterday, it can become one of two things. Either that number will become a VA, or that number will become a whole. A whole only comes when something canceled out on top and bottom, when there was a reducing or a simplification. Since nothing canceled or reduced, this graph will not have any holes. I just want to talk about that because that's going to be something we have to find in the future anyway. Okay? All right, also, another thing I want to point out that our book kind of makes you learn about is x equals 5, right? That's our VA. That means that there's a disconnect in the graph. There's going to be nothing exists right here. There's going to be a curve on this side and then a curve on this side of the VA where the other x values can create ordered pairs. So you're going to have two separate curves on your graph. When this number cannot equal 5 one time, we call that a multiplicity of 1. He was bad one time. So that means the number 5, he had odd multiplicity. That means that the graphs will shoot off to opposite infinities on either side of that VA. It means one side of the graph is going to shoot off to positive infinity, and the other side of the graph is going to shoot off to negative infinity. That's a good clue to know because it makes filling in the graph that much easier for us when we know little clues like that. So again, because he was only a bad guy one time, odd multiplicities, Odd multiplicities always have curves that go to opposite infinities on either side of that VA. All right, let's go to, I don't want to do all of them because I'm going to run out of time. So what I'll do is anyone that I skip in class, it'll be filled in on your notes for you guys to see on your notes. All right, so let's go to this one. All right, so the first thing I would ask you to do is FDR, factor, find your domain, then reduce. So I'm going to factor my top, difference of 2 squares. Guys, I just want to give you a heads up on your homework. I think the sum or difference of 2 cubes makes a comeback. So you might want to make sure you know how to factor the difference of 2 cubes or the sum of 2 cubes. It's just a formula. All right, over, then I'm going to get what? X plus 7, X minus 3. It's really tempting to want to cross stuff out, but you have to hold back. You factor, you find your domain, then you're allowed to reduce. All right, so my domain. Who would I not want to plug in for X? I do not want to make my bottom equal 0. So that means I definitely don't want X to be -7 because that would make that factor 0. And then 0 times this would be 0. And I definitely don't want to make this factor 0. So that means X cannot be 3. So right now you have 2 numbers that you would never want to plug into this function. So you have 2 bad guys. So now our domain is definitely going to be X cannot be -7 and X can't be 3. So that means it can be any number from -infinity to -7, union any number from -7 to 3, union any number from 3 to infinity. All right, thumbs up. Everybody still good? We're okay? All right. So now that you have found the domain, now you're allowed to go back and reduce. So now when I go and I look at this, a factor of X minus 3 and X minus 3, guys, they're going to cancel out. And that's going to leave you with an easier, smaller function to work with. And why wouldn't you want to work with something that is smaller and easier to work with? So that means for the rest of the problem, you could work with this function. Okay? So now, guys, look at this reduced function. Who still looks really, really bad? -7 still looks really, really bad, right? Because -7 would make the bottom equal 0. So that means the bad guy that is still there is going to end up as a vertical asymptote. You're never going to be allowed to plug -7 in and get a good guy out. So that means there's a brick wall where your graph cannot exist. So that means you're going to have, I'm running out of room, you're going to have a VA at X equals -7 at that line. There's going to be a vertical asymptote. Okay, but guys, -7 was not the only number who wasn't in our domain. 3 was also not in our domain. But does 3 look that bad anymore? No, 3 actually looks like, wait, is 3 okay now? No, he will never be okay. But because he doesn't appear in the function anymore, he doesn't act as a vertical asymptote, he acts as a hole. So that means you're going to end up with a hole at the point when X is 3, the bad X value, and then you have to plug 3 in to see what number comes out. 3 plus 3 is 6, 3 plus 7 is 10, what's that going to be? 3/5? And now you have a hole at the point 3/3. So like I said, if you are a number not in the domain, you either become a VA or you become a hole. The VA comes from the one that is always bad, even after the reducing. The hole comes from the one that passed out. Can I get a thumbs up that everybody's okay with that? All right, now, I also want to point out, X could not be -7 just one time. He was only bad one time. Just pretend, what if you had an X plus 7 and another factor of X plus 7? Then -7 would have been bad 2 times, right? So he would have had a multiplicity of 2. Well, since he was only bad once, that means he has odd multiplicity. And again, what that is telling you is any VA that had odd multiplicity, it means the curves on either side, one curve has to shoot off to positive infinity, the other curve has to shoot off to negative infinity. Oh my God, I don't have to wear my mask, there's nobody here. So that's what I want you guys to realize is you can tell the curves are going to go in opposite directions because of that odd multiplicity that VA had. And I'm telling you, that's going to be very nice when we start filling in the graph later to know that clue. All right, guys, I'm going to skip the last 2. I'll fill them in on your notes just so you have those examples. But just so I can get to the HAs, I want to go to the next page of our notes. So let's scroll down. And I just also want to make a note that, guys, these rational graphs, they're allowed to have no VA and they're allowed to have no hole. So it's not like they have to have a VA or they have to have a hole. That's not the case. Sometimes they don't have any. But these graphs will have an HA or an OA or that fourth kind of asymptote that we don't actually get into. That's not a line. It could be a parabola. It could be the graph of a cubic. We don't do them, but there will be some type of horizontal type asymptote, all right? All right, here we go. So this one says, find the horizontal asymptote or the oblique asymptote. Unfortunately, the VA to me is easier in the sense that I just find the bad guys that make the bottom equal 0, and they either become a VA or they become a hole. The HAs, the OAs, guys, they're based off of a set of rules that you guys have to memorize. But the rules come from just common sense math. So look here. It's all about the degree of the top polynomial and the degree of the bottom polynomial. And in the future, you can work and find this information out with the reduced function or the original function. So since it doesn't matter and we're not actually graphing it, I'm just going to work with them as is. I'm not going to worry about having to break them down or factor them because this information never changes whether you use the original or whether you use the reduced. All right, here we go. So right now I have, if you can read it, this is a degree 3 polynomial over a degree 5 polynomial. So clearly the bottom degree is bigger. So we have the denominator degree is bigger than the numerator degree. So there's a rule that we have to follow as far as whether it has an HA or an OA. Well, guys, if the denominator's degree is bigger, it has an HA. There's no OA. They can't be both. It's either HA or OA. So this one has an HA according to the rules. So guys, if you think about it, the horizontal asymptote or the oblique, they're trying to figure out at the end of the graph, the end behavior, what's the Y value heading towards becoming, right? So at the end of the graph, when you are working on a graph, guys, the ends, X is huge. X is going towards infinity and X is going towards negative infinity. So you'll be plugging these really, really gigantic X values in when you're at the end of the graph. So think about it. When you start plugging a huge number in, this becomes insignificant and this becomes insignificant. It's really about those leading power functions. So if I plug a big number in here and raise it to the third power, yeah, it's going to be a really big number. But if I plug that same really big number in and put it to the fifth power, holy crap, that bottom number had just became so much bigger than the top number. So when the bottom degree is bigger, it's always going to be a smaller number on top divided by a huge number. And guys, if you take a smaller number and divide it by a huge number, take 1 and divide it by a million. It's like 0.000000000. So when you take a small number and divide it by a huge number, and that's what's going to happen every single time the denominator's degree is bigger, you're going to head towards the Y values becoming 0. So that means you're going to have an HA at the x-axis where Y equals 0. And that's exactly what the rule says. The rule says when the bottom degree is bigger, your HA will be the line Y equals 0. And that's just a rule you have to memorize. But this helps me remember, when the bottom degree is bigger, this is going to be a big number and a small number. A small number divided by a big number has to head towards equaling 0 as x gets bigger and bigger and bigger and bigger. All right, and then that means since it has a horizontal, there's no oblique. There cannot be both. Okay. Then let's go to part B. Look at this one. They want you to find out whether this one has a horizontal asymptote or an oblique asymptote. Well, again, it comes down to the degrees. I have a degree 2 polynomial over a degree 2 polynomial. So now the degrees are equal. The denominator's degree equals the numerator's degree. And there's a rule as to what your HA or OA has to be. Well, the rule says when the degrees are equal, there's a horizontal asymptote, there's no oblique. So we're going to have a horizontal. And when you think about it, the horizontal asymptote is predicting that end behavior. So X is going to be really, really, really big. So when you plug really, really big numbers in, this is going to become insignificant, this is going to become insignificant. It's all about, you're going to end up with 8x squared divided by 4x squared. Well, guys, if they're going to be the same degree, you're always going to have that common factor that cancels out, and y is going to head towards whatever 8 divided by 4 is. It's going to be the ratio of those leading coefficients. So in this case, we're going to end up with a horizontal asymptote, and as x gets really, really big, the y value, f of x, is going to head towards equaling 8 divided by 4. So it'll be the line, 8 divided by 4, it's the line, y equals 2. Okay, can I get a thumbs up if you kind of remember these rules from last year? Because I believe you did do these graphs last year. Are we okay? All right. All right, here we go. And that also means if you have a horizontal, you do not have an oblique. You cannot have both. It's one or the other. Okay? All right, let me try and get this one done, and then hopefully we should be good to go. So now look at this one. If they ask you to find the horizontal asymptote or the oblique asymptote, well, again, it's all about those degrees. So I have a degree 2 polynomial over a degree 1. And I get it. In the next section, when we start putting the graphs together, we'll probably have factored, found the domain, reduced this. You can use the reduced version to get your HA or OA, or you can use the original function to get your HA or OA. Luckily for us, that won't matter, but normally if it did reduce, you'd have an easier function to work with to go find that HA or OA, okay? But the degrees will always stay the same. If the top degree was bigger than the bottom, then even in the reduced version, the top degree will still be bigger than the bottom, so it's okay. All right, we have a degree 2 over a degree 1. So now the numerator's degree is bigger than the denominator's degree, but it's only bigger by 1 degree. That means, according to our rules, if it's only bigger by 1 degree, then you don't have a horizontal asymptote, you have an oblique asymptote. And an oblique asymptote, guys, it's a slanted line. So it's just a fancy word for a slanted line. Some people call them oblique asymptotes, some people call them slant asymptotes. Okay. Well, the reason we end up with an oblique asymptote and not necessarily just a number is, guys, think about it. If you have a bigger degree on top over a smaller degree on bottom, that means when you start plugging these x values in, you're always going to end up with a bigger number on top because his degree is bigger over a small number. Well, guys, I don't know about you, but that's exactly how division is supposed to work. You're supposed to take a big number and divide it by a small number. So if that's the case, we would have to actually divide this to see, hey, what number are they becoming? So in this case, you're actually going to have to divide these polynomials to see what they're heading towards becoming. We know if the bottom's bigger, it's going to head towards 0. We know if they have the same degree, they're going to have that common factor that cancels out, and I can just use the leading coefficients. But if the top is bigger, I don't know what they're heading towards dividing to. So you're going to have to long divide them and see what polynomial they are heading towards becoming. All right, so we're going to have to find out how many times, I'm just going to put long divide is the rule. We're going to figure out how many times x minus 1 goes into 2x squared minus 3x plus 2. Now, some of you might say, well, I could factor this and figure that out. They don't all factor and cancel, so I'm just going to do long division because it's going to work for every single type of problem. How many times does x minus 1 go into 2x squared? Now, guys, this is important. It's kind of like the synthetic division. And you could synthetically divide, but you can't synthetically divide here. So you have to know your long division. You have to look for missing terms. The number, the polynomial put in here, you want place values for anything that you might end up with in your answer. So if it's a degree 2, you better have an x squared, an x, and a just number. If we didn't, you'd have to fill in zeros. And you'll see it when I show you that one. Okay, so how many times does x minus 1 go into 2x squared minus 3x plus 2? All right, well, how many times does x, the first term, go into this first term, 2x squared? X times what gets you a 2x squared? It's going to be a 2x. So you put your x's above the x's as like a placeholder. All right, that's the division. Now we multiply. 2x times x is 2x squared. They have to match in this long division process. If they don't match, then you didn't pick the right term up here. All right, 2x times negative 1 is negative 2x. All right, now we subtract to see what's left. Just don't forget to pick up that subtraction each time. 2x squared, take away 2x squared, they cancel. That's what you want. If that didn't happen, you didn't pick the right piece. Negative 3x, subtract negative 2. Subtracting negative 2 actually turns into a plus. So negative 3 plus 2 is negative 1x. And then you would bring down everything else left, and we're going to do it again. Okay, how many times does x go into a negative x? X times what gets you a negative x? A negative 1. So now we need a negative 1 above our numbers. All right, now we multiply. Negative 1 times x is negative x. See how they match? If they didn't match, then you didn't pick the right piece. Negative 1 times negative 1 is positive 1, and then we subtract to see what's left over. All right, negative x, subtract negative x, negative turns to plus, so they end up canceling. 2 subtract 1 is 1. So that's a remainder. So don't worry, guys. They're probably not going to divide in evenly. The remainder gets dropped. The reason the remainder gets dropped, if you remember, you would write the remainder as plus the remainder, 1, over who you divided by, x minus 1. But you're trying to figure out what the graph is doing when x gets really, really big, right? So if I plugged a really, really big number in for x, what's 1 divided by a really, really big number minus 1? Guys, this is going to head towards a 0. So we drop the remainder because it's insignificant when x gets really, really large. So that means your slant asymptote, your oblique asymptote, is the line y equals 2x minus 1. So as x gets really, really large, the ends of this graph are heading towards this slanted line. Okay? How does that feel? Is everybody okay? All right? Okay. We only have a couple minutes left, so what I'm going to do, guys, is on the bottom of the notes I never planned on getting to today, those pictures, don't worry about them. I'm going to fill in this one before I take a picture of it, and I'm going to go back to the front of the notes and fill in those other 2 examples that I skipped, so you'll have the work for them all written out in case you need to see those examples, okay? All right, so remember, a graph will have an HA or an OA, or that different type of asymptote, but I never assign you those ones when the bottom and when the top is bigger by more than 1 degree. Don't worry, they don't come up. All right, but then the VAs and the holes, you may not have one. So you could be clicking no VA, no hole. That's fine. But these ones, you should end up with an HA or an OA, okay? All right, does anybody have any questions for me? Okay, you have, I believe yesterday's homework on day 1 is due tonight, and then day 2 is due tomorrow night, and I believe it's 11 or 12 questions again, okay? Guys, thank you for coming in. I appreciate it, and let me know if you have any questions and I can help with anything, okay? All right, I'll see you guys tomorrow.